Hello, calculus gals! Today's lesson is all about interpreting the derivative as representing velocity and some other rates of change. That means we're going to look at some things today like the instantaneous rate of change, motion along a line, viewing acceleration as the second derivative, modeling vertical motion, modeling particle motion, using the derivative as a measure of sensitivity to change, and calculating marginal cost and marginal revenue. So in this video, we'll look at some applications of derivatives as functions, and we'll use them to represent the rate at which some things change in the world around us. We're used to thinking about something changing with respect to time, so like speed is the distance that you travel over time. But we can look at how things change with respect to other variables. So for example, a doctor might study how a change in dosage of a medication can affect the body's response to that medication or drug. An economist can study how production costs of different things vary with the amount that they're producing. So if we take our difference quotient that we've been working with, and we interpret that difference quotient as the average rate of change of the function f over the interval from x to some point x plus h, we can interpret its limit as h approaches 0 to be the rate at which f is changing at the point x. So that's what our definition of instantaneous rate of change here says. And something to note for all of these examples that we're going to work through today, we usually say rate of change, even though we actually mean instantaneous rate of change. So you'll always see just rate of change, and that's always going to mean instantaneous. So it's just common practice to just drop the word instantaneous, but we have to remember that that word is implied. It's not the average rate of change, it is the instantaneous at that instant, at that moment. Okay, example 1 is about enlarging circles. So we have 3 parts to this problem. A says, find the rate of change of the area A of a circle with respect to its radius r. Part B says, evaluate the rate of change of the area when the radius is 5 and when the radius is 10. And part C, if we know that radius is measured in inches, and then area is going to be measured in square inches, what units are going to be appropriate for dAdr? Okay, so our formula for the area of a circle is area is equal to pi times the radius squared. So this shows how area is related to the radius. So if we calculate the instantaneous rate of change of A with respect to r, that means what we're going to do is we're going to find the derivative of A in terms of r. So we're finding dAdr. So the derivative of the function a, which is pi r squared in terms of r. We know how to do this. We can break this down into parts. We know how to do something to the power of 2, and then we know what to do when we have just a constant being multiplied. So the first derivative of pi r squared is going to be pi times 2r. We can also rewrite that as 2 pi r. And incidentally, 2 pi r is the formula for the circumference of a circle. So the derivative of the area is the circumference. Okay, for part B, when the radius is 5, we need to find the rate of change. So radius is 5. We're going to plug that in here. So we know that's going to be 2 times pi times 5, or 10 pi. Usually I leave things in terms of pi, but if I'm working with measurements and I want to have an idea of what exactly 10 pi means, then I'm going to multiply it out and get a decimal form. So 10 pi is approximately 31.42. And if our radius is 10, we're going to plug that in and we get 2 times pi times 10, which is equal to 20 pi. which is approximately 62.83. And we can see that it makes sense that the rate of change that we just calculated is bigger when our radius is bigger. So if we look at this circle right here, we can visualize the radius and the area changing. So as I increase my radius, the area of the circle entirely changes. The same change in radius actually can bring about a bigger change in area. So if I actually look at these two pictures, this circle over here on the right, this one right here, we can see that the radius is changing by about the same amount every time, and as we increase it the same amount, we're actually getting more and more area change. We could flip it around and keep our area change the same, and our radius would have to get different. It'd be smaller and smaller. Okay, time for part C. What units are appropriate for dA, dr? So if we think about it, A is in square inches, R is in just inches. So the units we want to use for dA/dr is square inches of area per inch of radius. Another use of derivative is velocity, or motion along a line. So let's imagine we have a line like this one. This is an S-axis. It's coordinate line, so we can find the coordinates of a point anywhere along the line. So we can write the position of an object as a function of time. So it's moving in time and in space. So we can say its position at time t is this function right here. S is equal to f of t. We can call how much the object moves its displacement. Displacement's another word for that. And displacement happens over an interval of time from t to time t plus some small delta t, some small change in t. So we can use this to demonstrate what the displacement is. So we can put all that together and we can say that the average velocity of this object over that time interval is the derivative of the position functions s equals f of t with respect to time. At time t, the velocity is this right here. So to find the object's velocity at the exact instant t, we take the limit of the average velocity over the interval from t to t plus delta t, as delta t shrinks to 0. And that should look familiar. It's our derivative again. And again, usually we call this just plain velocity when we mean instantaneous velocity, so don't forget that that is implied. Okay, moving on to example 2, finding the velocity of a race car. This graph shows the time to distance graph of a race car. You can see on our t-axis we have elapsed time, so that's our x-axis over here. And then on our y-axis, our s-axis, we have distance in feet. We can use this graph to help us find a whole bunch of things. So if we want to know what the average velocity for the 3-second interval from time is equal to 2 to time is equal to 5 seconds, so here is where our time is 2, here is where our time is 5, we're actually finding the slope of a secant line. So we can find the slope of the secant line, that's our average velocity for the interval t equals 2 to t equals 5. In this case, that average velocity on this interval is about 100 feet per second or 68 miles per hour. If I were instead to find the slope of the tangent at this point P, so this line right here, that slope is going to tell us basically what the speedometer reading is. exactly at time is 2 seconds. So you can see that the car is accelerating as it goes, and at 2 seconds, it looks like this race car is going about 57 feet per second or 39 miles an hour. So the acceleration for this period shown is a nearly constant 28.5 feet per second during each second. So you can see it's almost like an exponential type of curve, which that's about 0.89 Gs, where G is acceleration due to gravity. The race car's top speed is an estimated 190 miles an hour. So velocity tells us how fast something is moving, but it also tells us the direction of motion. So when velocity is positive, we say the object is moving forward. When the velocity is negative, the object is moving backwards. But if you think about it, if I were to drive a car backwards, my speedometer that tells me how fast I'm driving doesn't show negative 30 miles an hour if I'm driving backwards home. So we call speed, how fast something is going, the absolute value of velocity. We take directionality out of velocity, and that gives us speed. So here's our definition of speed. Speed is the absolute value of velocity. So let's use our idea of speed as the absolute value of velocity to interpret this graph. So this is a velocity graph. And so how we generate these things is, let's say we have a motion detector, and the student walks around in front of the motion detector, and it records their velocity at 1 second intervals for 36 seconds. So we store the data, and we can put it on our graphing calculator and use it to generate this time velocity graph. So let's describe her motion as a function of time just by looking at this velocity graph. We want to know specifically, when is her speed a maximum? Okay, so let's just look section by section on this graph. So she starts here, and her velocity is increasing. Then it stays the same. Then it decreases over a long period of time, increases again, stays flat, and then increases again. So when velocity is increasing or decreasing, that tells us about her speed. And the parts where it's flat also tell us something. So increasing means she is walking towards the motion detector. Then she stands still. Then she walks away some more. Then she turns around and walks back, stands still for a little bit, and then walks towards it again. So if we look, we were looking for approximately the fastest speed, and it looks like her fastest speed is going to be wherever her steepest slope is, so the greatest rate of change. So her greatest rate of change is about where she is moving backwards. It looks like right around here probably has the steepest slope of this entire function. So the rate at which a body's velocity changes is called its acceleration. Acceleration measures how quickly the body picks up or loses speed. So acceleration is the derivative of velocity with respect to time. If a body's velocity at time t is v of t equals ds dt, then the body's acceleration over time is actually the second derivative. So some of the earliest questions that motivated the discovery of calculus were ones that were concerned with velocity and acceleration. Specifically, they were worried about the motion of freely falling bodies under the force of gravity. Scientists like Aristotle, Galileo, and Newton all were fascinated by trying to come up with some mathematical descriptions of this type of motion. They worked experimentally and tried things out, and they also worked theoretically, just like doing the math to see what would work. So the formula that came out of their work is S is equal to 1/2 gt squared. And usually we describe this in words, saying that the distance a body released from rest falls freely is proportional to the square of the amount of time it has fallen. So in this case, S is distance, G is the acceleration due to Earth's gravity, and T is time. So the value of G in this equation depends on the units used to measure S and T, with T in seconds being the usual unit, we will have these following figures or values. So these are free fall constants for Earth, because if you remember, gravity is not the same around the universe and the solar system. So on Earth, gravity in English units is going to be 32 feet per second squared. In metric units, that's 9.8 meters per second squared. So usually this is pronounced feet per second squared. Sometimes you'll hear people say feet per second, and you could hear meters per second for this one. Okay, moving on to example 4, modeling vertical motion. A dynamite blast propels a heavy rock straight up with a launch velocity of 150 feet per second, which is about 109 miles per hour. It reaches a height of s equals 160t minus 16t squared feet after t seconds. So we know a few things. How high does the rock go? What is the velocity and speed of the rock when it is exactly 256 feet above the ground on the way up and on the way down? What is the acceleration of the rock at any time t during its flight after the blast? And can we figure out when will the rock hit the ground? So here is a diagram of what is happening with this rock. You can see it's going up and then coming back down. So if we think about a rock going up and then coming back down, we can remember that the instant when the rock is at its highest point is going to be the one instant during the flight when the velocity is actually equal to 0. And so at any time for this rock, our velocity is equal to ds dt, which is d dt of 160t minus 16t squared. So we can use the rules for differentiation we learned last week, and we know that the derivative of this is going to be equal to 160 minus 32t feet per second. And to figure out when velocity is 0, we're going to set this equation equal to 0. And if we solve this, we will find that velocity is 0 when t equals 5 seconds. So we can take this t equals 5 seconds and we can go back to our original equation and we can plug 5 seconds in, and then we can calculate the height of the rock at 5 seconds. So we will say S max is equal to S of 5, which is 160 times 5 minus 16 times 5 squared. And if we calculate all that out, we get that is equal to 400 feet. So the maximum height that this rock goes is 400 feet. Okay, let's go back and do part B. What is the velocity and speed of the rock when it is 256 feet above the ground on the way up, on the way down? So now we know we need to have the height is equal to 256, and then we will figure out what time is it when it's 256 feet up, and then as it comes back down, how long when it hits 256 feet again. So we can solve this by saying S of t equal to 160t minus 16t squared equals 256. Because we want to know when is it going to be 256. So we can move our equation around, and we end up with, if we put everything on one side, we get 16t squared minus 160t plus 256 equals 0. And then we do that because we can factor 16 out of this. So if we factor 16 out, we'll get t squared minus 10t plus 16 equals 0. And then we can factor this term right here into t minus 2 times t minus 8. And if we divided everything by 16, the 16 will disappear. Cancel out on this side, 0 divided by 16 is still 0. So we know that we're going to end up at 256 feet when time is 2, and again when time is 8. Now that makes sense if we think about throwing a rock up. It's going to cross 256 feet. It's going to max out at 400 feet, and it's going to come back down and cross by 256 feet again. So to find the velocity of the rock at each of these times, we already did our math and found the formula for velocity. So we know that we can just plug t equals 2 and t equals 8 into that. So velocity at time is 2 is going to be 160 minus 32 times 2, which is 96 feet per second. And if we do the velocity at time is 8, we get 160 minus 32 times 8, which gives us negative 96 feet per second. And makes sense. This is on the way up when time is 2, and this is on the way down when time is 8. So going down, negative 96, going up, positive 96. And if we were talking in terms of speed, we would say the speed of the rocket both of these times is 96 feet per second because speed is the absolute value. Okay, let's think about what is the acceleration of the rocket any time t during its flight after the blast, part C. So, acceleration is equal to the derivative of the velocity with respect to time. And so we're going to take the derivative d dt of 160 minus 32t. And if we take the derivative of that, we get negative 32 feet per second squared. Feet per second per second. So we can interpret that as the acceleration is negative 32 feet per second squared. And acceleration is always downward. When the rock is rising, it's slowing down. When it's falling, it's speeding up. Okay, if you are good and you followed along with all of that, if you want, you can look on page 137. And you can try questions 1 and 7, 9, and 13. And we will talk about what we learned tomorrow.